Thank you. Good morning, everyone. Again, I'm Chris Janz. I'm from Siena. I lead our market development organization, and SDN is a big part of my life now for a few years. You can guess from the term multi-layer in my title that my focus is on carrier wide area networks. Obviously, the wide area is where distance and therefore transport come into play. But generally, in looking at carrier networks, we find a few differences from the enterprise environment that has dominated the SDN space to date. First of all, there is much greater complexity. Not only do we have distance, immediately meaning we have more significant analog and transmission problems. We have multiple layers in the network. In the carrier environment, we have vastly greater scale. Though some data center networks are very great in scale, it's a different order again when we get into large carrier networks. We have multiple service types supported across many users, and this in a business environment where the network is a vehicle to sell services that have agreed characteristics and agreed pricing. All right, so this is an environment that does not change slowly. And I would hesitate to say that things have not moved swiftly with SDN in the carrier sphere only because the vendors are intransigent. That may be partially true, but the fact is that things change and evolve and money is spent in the carrier environment when the business executives see the business reason to spend the money. So SDN will happen in this environment when business executives see the business reasons. Now, what's exciting is I think we're seeing a lot of signs over the last 6 months that those business executives are starting to see the logic and get quite excited about SDN. So let me walk through first a little bit what the SDN value equation that they are starting to see and get excited about is. I think broadly now carriers accept that SDN is going to be key to solving two problems. And these are not any two problems. These are the twin problems that keep all carrier executives awake at night. The fact that their costs, both operations costs, OPEX, and capital costs, CAPEX, are rising at a rate with increasing traffic on their networks that is unsustainable. And it is unsustainable because their revenues derived from that traffic is not growing as quickly. So there are two lines, cost dollars or yen versus time, that are converging. And when those lines cross, these guys go out of business. Now, SDN is unique among things that they're looking at in being able to address all of these problems simultaneously. And it's that realization, I think, that is stimulating the interest that drives investment on the part of carriers. And we're in that phase now, if the early phase. Now, where does this power to address all of these problems come from? Right? The key, in fact, is in the word centralized and control. One of the features of SDN is that it can changes what we've called the control plane structure of networks. It at least partly centralizes the control plane processes of networks and also places them significantly in software. And this is the key. Let me focus on one thing first. That centralization creates the opportunity to place intelligence functions in software, and these functions are in fact the means of attack on many of the benefits promised, OPEX, CAPEX, and revenue. Now, how does that work? This diagram you will recognize. This is the Open Networking Foundation standard diagrammatic view of the SDN architecture. And you'll recognize it too from other talks throughout this conference. We have at least two software layers in this structure. This is ostensibly and certainly in a carrier WAN environment, overwhelmingly a physical platform. But this becomes a programmable platform where anything from partial to total control plane functions are synthesized now in this software layer. And the use of this total network platform from a service perspective is delivered directly over an API by other software systems. And in the carrier world, these would be predominantly the software systems that deal with the business side of service creation, right? Interface to customers, CRM, billing, the whole revenue service management problem. They provide the reason to commission connection services on the network, and this system delivers those connections. Now, one of the things we see in this system, obviously, is that it is a fully interlocked software-based system. And this stands the promise of manual processes bridging disparate systems and processes coming very significantly out of the path of customer to service to cash. Right? So automation in this system is really the key to OpEx reduction. And we shouldn't underestimate the importance of OpEx reduction. Most carriers will say that their OpEx is larger, is some multiple of CapEx for a given service environment. So that as things grow, the relative cost of OpEx increases, in fact, over time. So this is a compelling benefit of the SDN structure. We can also see that from a revenue perspective, because this service application layer is not only based in software, but it's completely and structurally decoupled from the control system, there's a lot more freedom to innovate at high velocity in the service creation layer. And carriers can do that directly. And of course, that's one path to revenue. But there's something else, and this is really the interesting part of the problem. When you look at this control system, which is now either significantly or partly centralized and placed in a software system, we call a control layer, you have two things that intersect. One, by definition, this system has global control of the network state, right? So in a sense, it has global control of supply from the network. But at the top of the structure, coming in over this API, is a global view of all the service demands being placed on the network. In other words, a global view of demand. Now, a single software system has those two views, which means that the software system can reconcile those two views. We have the capability now structurally to put software-based intelligence that can match supply and demand no matter the resources available on the network and no matter the changing state of the service demand map. And that's key to, first of all, CapEx constraint, right? It's very difficult with a static network that is difficult to reconfigure to deal efficiently with changing and unpredictable service traffic demands, right? Because the network state is really only optimized in terms of resource efficiency for a particular set of service demands. When they change, the network state, to remain efficient, really should change with them, right? And we have that capability in this system. We can continuously change the network state by software that is responding to the changing state of demand. And that's how you run the network hot, and that's how you defer requirements to pay money to add physical capacity to the network. You can also match supply and demand through pricing. That's economic-based supply and demand reconciliation. How do you price services in a dynamic environment? Well, you have the information you need to price services effectively, to create the greatest utility for consuming customers and the greatest revenue for the provider, right? So this ability is revenue impacting as well. In theory, we should have the ability, once we're operating in an SDN architecture, to create software applications that can be inserted, turned on, and immediately drag down the growth of CapEx and increase revenue generated from the network. it's not hard to see the appeal of that sort of function. A second aspect, sorry, pressed the wrong button. A second aspect is this idea of open architecture control systems. And this is the idea that, great, we put a lot of what controls the function of the network and how it delivers services in software. And that's desirable also because software is relatively easy to modify versus hardware or software that is interlocked intimately with hardware. Right? So there's an expectation that SDN will make the software that runs the network accessible and therefore innovable and modifiable, not just by vendors, but by providers themselves, that they can innovate, create, change their software systems, and do that with the objective of better controlling their business destiny. Right? All of those factors of services to revenue, pricing for revenue, cost controls, all of these things in principle come more under their control, their ability to innovate. And so their ability to design their business, its economic models, and its differentiation versus competitors is increased in an SDN world. And that is attractive to service providers. But this is only available when they can actually change the software they're given, right? Software that is monolithically wrapped and unchangeable doesn't do the trick. So what they really need is an open architecture system. Open here, but also open within the control system. As we saw, there's a great deal of business value, top line and path to bottom line, that can be created, determined, limited in this system. So the ability to innovate within this system is critical as well. Now, how does that happen in practice? I think the view of sort of a Lego block type of system is a good analogy of where the industry is headed. Basically, some industry agreement on what is the fundamental architecture of a control system, and particular to the carrier environment, ultimately. What are the key building blocks? How do those building blocks fit together? So think of internal interfaces and the like. And then finally, what are the pieces that are so common to every control system that there's industry efficiency in delivering those collectively through open source? Right, so we'd sort of see a future environment like this where the industry collectively is delivering standard foundations of control systems, keeping them up to date, where vendors and providers alike are able to construct their own specialty building blocks. These will be the things that, for a vendor, are most monetizable, that create the most particular value, that may be the hardest to build, that may repose on specialized skills. I mean, you saw the word real-time analytics, right? That's mathematics and computer science, largely. You might see vendors such as Sienna wrapping a particular offer sufficient to construct a carrier control system for a particular role and architectural view in the network. But of course, there's the freedom in this picture for individual service providers to really construct what suits their particular needs and to seek business value and differentiation versus their competitors. Okay. So we talked about partial centralization and move to software of control systems for networks. Now that by itself, does that impact the physical network? Well, over time, we would say the answer is yes. There are some good reasons why this change in the control plane structure will impact the network itself. First of all, there's an obvious, there are several factors that you could describe it best as centralized control not only allows in previously unavailable ways, but drives, creates logic around a certain simplification of the controlled networks. One manifestation of that is a logical trend toward not only standardized, but essentially programming-oriented control interfaces to the network versus the existing management interfaces, which are there to deal with existing embedded and protocol-based control planes. Okay. A second simplification will be the removal of what you could call point or processing functions. Think firewalls, content filters, those selectionable, service customizing point functions that no longer have any logic being within the network itself, that can be moved to create efficiencies and flexibilities and economies into virtual implementations in data centers. And this is what we call NFV. And there's one other factor which is roughly under the heading of layer convergence. That in that carrier environment where we have multiple layer networks, which still remain very distinct and siloed in how they are operated, there's the opportunity to drive a greatly beneficial convergence of those layer networks, where the convergence is driven not by the traditional logic of I can get rid of boxes by putting multiple layer functions on a single box, although I would argue that that logic is amplified, but a convergence driven effectively through the control paradigm, because the SDN structure makes options for that available that were not previously available. Okay. Let me revisit briefly the whole question of multi-layer. And I want to touch on what people have called the inverted pyramid of network layer economics. And it's simply this idea that if you have a bunch of network traffic that wants to get from point A to point B, it is cheapest to put all of that traffic onto a light pipe and go straight between the 2 points. That is cheaper than the next cheapest option, which is to put everything on a circuit and then put it on a wave. Less economically efficient still is to pass through multiple switches and switch ports on the path from A to B. And least sensible of all is to pass through those multiple switches, each one of them touching an IP-based control plane, right? Now, obviously, you need multiple layers because you need levels of granularity and change to construct services, but this basic picture is accepted really by every carrier on the planet. They voted with their money. This is the reality of wide area networks. Now, what's interesting about what SDN can do for this picture? Let's look at the transport, or what we call the transport network. Originally, we had really a routed packet infrastructure, which was the service delivery vehicle. But the routers had to be connected because there was distance, so there was a need for an optical network, a transmission network. So we had two networks connected, cooperated, and in practice what we would do, we would take the topology and traffic map for this layer, and we would go off and plan an efficient wave network to interconnect those routers. Now, what's happened over time, and this is really largely the state of things today, by adding circuit, that is OTN granularity, to this system, we can deal more efficiently with things like mismatch of router and wave speeds. But by adding reconfigurable capabilities on both of these layers, we add flexibility. And that means that we can reconfigure the transport network to remain an efficient transport network even as the client traffic map may evolve. Now, this is really the status quo in the carrier transport network landscape. So we have evolution capabilities through reconfiguration, but still essentially manually driven. There's a presumption that those changes are relatively slow. Now, the world we're heading into, those changes will be increasingly rapid, increasingly large, and increasingly unpredictable, We have mobility of endpoints, and that's not just mobile consuming devices. That's mobile virtual machines and associated information stores that source the flows. That's increasingly large traffic flows, that is machine to machine within the cloud, for example. And we have not only mobility, but increasingly self-service consumption models driving unpredictability. So the pace of change is going to get faster, and what we really want is to push those granularity and flexibility options even further. And we can do that by adding packet capabilities to the circuit optical transport network, increasing granularity, and using SDN with its capabilities to intelligently and autonomously change network state to cope continuously with the faster changing traffic demand, right? So in other words, there's the possibility to continuously maximize this inverted pyramid economics in a dynamic service environment. Additionally, this network becomes a completely sufficient delivery vehicle for connection-oriented services. There's no reason to rely on this network with its connectionless rooted processes to construct the control plane for connectionless services. We can do that differently in an SDN environment. Okay. Now, how would you actually do this? How would you co-control the layers to achieve this effect? And how would you do that in an SDN world better than you can do without SDN? Well, let me construct a simple picture of not only one way this might work, but a way this probably will work in many cases, right? There's rapidly increasing discussion about this model out in the landscape. So Martin talked this morning about the difference between SDN and virtualization, but he also suggested correctly that they largely go together. And that allows us to say you can really define a controller as something that manipulates real resources below, but offers a different view, effectively a view and control of virtualized resources north, right? Now, you can place different networks under different controllers, right? And there's often very good reason to do that. As Justin showed, I mean, are you really going to put a data center LAN under the same controller as a carrier core network, et cetera, et cetera? There's probably, in most cases, very good reasons to partition those problems, right? But having done this, you can now use essentially orchestration functions, things that bring together needed sets of virtual resources to solve a given problem. For example, OTN optical and transport packet components of the network can be co-controlled with this sort of structure, right? And a collective northbound view provided by this orchestrator. This can be cascaded as far as you want, right? You can deal with a client packet network in a similar way through an orchestration function. And what's beautiful about this is it's completely flexible. You can really draw a dotted line around any group of controller and orchestration blocks and call that a controller for the relevant domain, right? So this, for example, becomes the effective centralized controller of what can become, but need not necessarily be, a converged, physically converged packet OTN optical network. And this is the sort of scheme we see increasingly thought of. The contrast to this scheme, the status quo, is something like GMPLS, right, which takes the distributed IP-rooted control plane of this network and attempts to extend it across this boundary. That's been the industry-preferred approach. Many trees have been felled and intellectual cycles exhausted in solving this problem, but it's had very little purchase in actual deployment in carrier networks. For a lot of reasons, most of which are addressed by the relative flexibility and simplicity of this scheme. Okay. Additionally, around a defined controller structure, you can associate the sort of intelligence functions that I referred to earlier. And in a multi-layer network controller, an example of that might be a multi-layer network optimization application, right? Something which can look at the provisioned state of all of the layer networks, that has a view of all of the service demands, and can influence the operation of this orchestrator, always to use the least network collectively across these different layer parts of the same network. Okay. Now, as an example of this in practice, I show here a testbed that Sienna is putting in place with a series of research and education community partners. Internet 2, you will certainly have heard of from the US. Canary, its counterpart in Canada. This is a packet optical 3-layer wide area network. It is all OpenFlow controlled. Not that we see OpenFlow necessarily and instantly and ubiquitously going into the carrier world, but if we accept the logic of a trend there, right, let's see what's possible immediately with pure OpenFlow control of large-scale pure OpenFlow packet switches from Sienna, but also packet optical products, large layer 1, layer 0 reconfigurable switches, and our 6500 packet optical platform with layer 0 and layer 1 reconfigurable characteristics, and also layer 2 elements controlled with OpenFlow in particular places. This is all controlled by our prototype open architecture SDN controller using available open source components, a partly distributed architecture, but with global control of state, with a multi-layer path computation engine, right? So co-controlling with a methodology similar to what I showed on the prior slide, intelligently co-controlling all of the configurable elements at all 3 layers, and presenting a very abstracted northbound interface to consuming applications. Right? Those consuming applications, for example, cloud orchestrators simulating a cloud or content service environment. Also, a client packet layer, right? So in other words, this network as infrastructure, transport infrastructure under a routed packet layer, but with the mechanism of co-control being, as I showed in the prior slide, through that northbound interface. And within this structure, we have 2 prototype intelligence applications. These were chosen to demonstrate conclusively benefits in both the CapEx constraint and the revenue promotion camps. This multi-layer optimization function is doing exactly what I showed on the prior slide. Right? It is continuously computing the optimum network state with use of resources across 3 layers given service demands. It is influencing continuously the path computation engine behaviors in order to adhere closely to that optimum state. And it also has the capability to force regrooms under policy selective control of the network in cases where there may be a significant divergence between the actual network state and the optimum network state. Okay? And what we'll show with this is 2 things. Not only that it's possible with an SDN structure to build an optimizing application, insert it in the structure, flip the on switch, and presto, you get an efficiently optimized network under all circumstances, but also that the multi-layer version of that will deliver a more efficient network result, a lower cost network result consistently versus a single layer optimizing application. The second thing that we targeted is looking at the revenue side, and it's doing precisely that pricing-based supply and demand matching I referred to earlier. For example, in a cloud service environment where we have transactional requests of the network to support cloud bursting, right? Those are transactional dynamic purchases. How do we price network services in that environment? Well, that's what this application will seek to do. It will study demand-side factors. What demands do groups of users present on the network? Gain a predictive capability, and also understand pricing sensitivities on the parts of different consuming customers. We'll also study the supply side. Where and when on the network is demand high and demand low? And pricing can be used to attract demand to underutilized resources and to capitalize for revenue on high demand, both in places on the network and in time, right? So here too, the objective is to show that yes, with an SDN architecture, you really can construct a software application, insert it into the environment, flip the on switch, and not only make more money, but make as much money as it is possible to make, given the service mix, the consuming customers, and what they are willing to pay. And again, those are precisely the kinds of business impacting values, benefits, and impacts that carrier executives now see truly are possible with SDN. And that's what's opening the wallet to look at these technologies and to see what can be realized and how quickly. All right, I hope that was interesting, and thank you for your time.